Awesome. Well, thanks for the intro, Aaron. So yeah, the agenda for today is generative AI. We're going to be talking about a whole bunch of different dimensions associated with generative AI. We'll talk about foundation LLMs first, the more general purpose and non-reasoning LLMs that we commonly use, ChatGPT and Claude from Anthropic, Llama from Meta, and the like. And then we'll go over to grounded LLMs. How do you take a foundation model and get it to work for you, for your use case, right? So that's the process of grounding these models. And there's a whole bunch of different techniques. So we'll cover them individually. And then we'll also look at a comparative analysis of all of these techniques to see when to use which. And then once we're done with that, we're going to talk about the heart of today's lecture, which is reasoning LLMs. And these have picked up a lot of good traction thanks to DeepSeek R1. So we're going to spend most of today's time talking about reasoning. And there's a whole bunch of different techniques, showing up in the field beyond just R1. R1 came a couple of months ago, and there's been a lot of momentum since then in this area. So we're going to touch upon some of those newer methods as well. There's also a slide I have that talks about how to actually utilize, some of this technology for, use cases in your labs and your research areas. So how do you democratize this enough to, leverage it for your use cases and projects with students, for example? So we'll touch upon that as well. And then I've put together some top-level application areas where we can utilize some of this technology, especially the reasoning aspects, both for technical explorations and non-technical explorations. And then finally, we'll conclude with a list of pointers. So if you guys want to go deeper into a particular area in any of these areas that we talked about, I've included a list of papers that you can start off with, you can go through. I've also write a whole bunch of primers online on most of these areas and a lot more. So I've got some pointers to those primers as well, in case you want to go deeper. But yeah, this is the agenda on the right here, and we're going to go clockwise, starting with foundation LLMs. All right, with that, let's get started. So frontiers of generative AI. So like I said, this field has gotten a lot of traction recently over the past 3 years or so. Generative AI has sprung up as, the method of choice to implement a lot of workflows, whether it's in the industry or in, personal projects or academic projects. It's everywhere at this point. This technology is transformational. The applications are endless. So, obviously leveraging, such a powerful technology comes with, also understanding what are its limitations and what are areas where it can do a good job at, and, the areas where we need to, put in special care. For example, hallucination in especially medical context, for example, is a big challenge. But we're going to touch upon a whole lot of these areas, and we'll get started with foundation models first, like I mentioned earlier. So getting into foundation models, like I said, I'm going to do an overview for most of these areas, but spend a lot of time in the reasoning aspect because that's more recent. That's where a lot of recent traction has been in the field. We'll talk about reinforcement learning and a couple of different methods to leverage reinforcement learning. But let's get started with a quick overview of foundation models. So the transformer architecture is what started it all back in the day, back in 2017. This paper basically implemented the model on the left that you see here in the diagram. And, the first half of this architecture is the encoder, which we'll touch upon in detail in the next slide. And we've got the second half of the architecture, the vertical half, which is the decoder, which is also, I've got a slide for that as well to get into detail. But as far as a quick overview of the transformer is concerned, the architecture basically said, the idea was, you can transform a sequence into another. And when I say sequence, it could be literally anything. It could be text being translated from one language to another, which is what the paper actually experimented on. But you can apply the same idea to other modalities, to images, to even text to image as well, which is a common use case for image generation, for example. So feed in, a string of textual tokens, and the model basically generates, image patches at the output, right? Or even at the pixel level or patch level, depending on what the implementation is. But you can go from an input sequence to an output sequence, irrespective of modality with this architecture. So this was the biggest selling point of the transformer architecture. So not limited to text in any way, which is what the original paper proposed it to be. But there were follow-up works. Vision Transformer came along in about, I think, 2020. And then, we've applied this architecture to video, audio, all kinds of different modalities. And, self-attention is basically at the heart of the transformer architecture that, differentiates, this architecture compared to prior architectures. So the idea is that feeding in an input sequence, the transformer architecture learns to figure out how each token, each unit of the input sequence relates to other tokens, right, or other aspects of the input sequence. And as it learns these relations, it's able to understand the input sequence better, and that helps it generate an output sequence that is grounded or is conditioned on this input sequence. Go ahead, Aaron. Yes, for sure. So a token is a fundamental unit of a input sequence. So given a sentence, for example, so let's take a quick example. You've got the quick brown fox jumps over the lazy dog, right? So standard input. What tokenization basically does is it figures out the fundamental units in the sequence by breaking these words up into units that help it easily understand in relation to other words within the same input sequence how one token attends to another. So it's essentially breaking down these words, and in some cases, it could be the same word that is the token, so there is no breaking that happens if it's a very simple, simplistic word without, say, a stem, for example, right? So, for example, if there's a word like running, for example, it breaks it into run and ing. So, it's easier for the transformer to understand that there is, that somebody is running, and it is in the positive, it is continuously happening. So it's, it's a verb in that sense. And the beauty of tokenization, the reason why we do it is, especially at the subword level, transformers and a whole lot of recent architectures do tokenization at the subword level. So they break words into different units, like I mentioned. There's also tokenization at the character level. So you could break the whole sentence into individual characters. But then you let go of some notion of, there's no semantic aspect to it then, right? Because you'll have individual characters being tokenized. But with the subword level tokenization, the reason why, it's a big reason why these architectures work pretty well, is because when we encounter rare words that the model hasn't seen during training, it's able to put two and two together by breaking down these rare words into different units, and this helps it connect the dots pretty quickly. A good example is the word auriferous, which generally means attractive or pleasant, right? If a rare word like this hasn't been encountered by the architecture during training, it's able to split it into auri, for example, and ferrous, and put two and two together. So aurum is, I think, the metallic element name for gold, for example. But understand that there is an element of something being attractive or pleasant to it, right? So it's able to put two and two together pretty easily. So that's an example of where tokenization is helpful. And all of these architectures at this point, not limited to transformer, everything goes to tokenization. So we had the same thing with prior architectures as well in the field. LSTM units, for example, or GRUs or RNNs, everything goes to tokenization. But with the level that we have here, the scale that we have here with the transformer and the amount of the vocabulary size that we can have, we can go from multiple languages to multiple modalities, all within the same architecture. So whether it's images, different languages all around the world, everything can be packed in one place also. So yeah, coming back to the transformer, like I said, self-attention is at the heart of the transformer, and the encoder and the decoder connect with this connection in between to something called as encoder-decoder attention, also called cross-attention. So that's where the decoder on the right basically accepts the the synthesized form, which is the output of the encoder on the left. So the connection that you see going from the left to right, that bridge, is cross-attention. And this helps the decoder, which is responsible for generating tokens one after the other in an autoregressive way. This helps it look at what the encoder has synthesized after taking in the input sequence in an encoded form. And that lets the decoder generate tokens one after the other in an autoregressive way. So that's overall the architecture. This is a very top level overview because I have a slide each for the encoder and decoder coming up next. So we'll dig into each of these blocks. But yeah, let's get into the encoder. So like I said, the block on the vertical block on the right, that is the encoder, the one that's outlined here. And the idea behind the encoder is, something very simple. It says I'm going to take in inputs down there, right at the right at the bottom, and that's going to basically be converted into embedding forms. That's an input embedding, which is essentially a sequence of numbers. So we're basically learning an embedding per token. So it's at the token level, and an embedding is essentially a set of numbers. So it's a vector corresponding to each token, which is initialized randomly. And as we train the transformer architecture, it trains these numbers to resemble what these individual tokens mean. So the semantic content of these tokens, which is essentially a function of other tokens in the same sequence. So it derives a lot of this semantic notion relatively, looking at other tokens within the input. And that gets baked into the embedding of that particular token, right? So that is the input embedding. And then what we do is we add up the positional encoding to that input embedding, because the transformer inherently has no notion of positions of tokens. So it doesn't know which token came prior, which token came after. We need to explicitly add a positional encoding to this to the input embedding. And there's various ways to model that as well. The original transformer encoder had a certain proposal. It was basically using a sinusoidal wave, sine and cosine waves, to model these positions for individual tokens. But we've had a lot of papers come through since then, where instead of absolute numbers, we've looked at relative tokens, relative positions. And then most recently, we've got rotary positional encoding as well, which is used in Llama and all of the leading models right now, whether it's Claude or GPT, even though they're closed source. The hunch is that they're using it as well. It's standard in the field at this point. But the idea behind the positional encoding at top level is to make sure that the transformer architecture understands the notion of positions of these tokens. So it understands which token came prior and which tokens came after a specific token. Now, this gets fed into the multi-head attention layer, and this is essentially the self-attention, concept that we talked about in the prior slide. So this is the heart of the transformer architecture. This is where a lot of that relational learning happens. This is where the transformer architecture learns to semantically understand what a token likely means based on other tokens in that same sequence. So this is where the relational learning is happening. And there's a lot more details here. Query key values are what the transformers inherently use. So this is another layer of abstraction that they add to this learning to figure out, what are some queries that it can learn. The input is basically the query, the input tokens. But what's a kind of an internal hash map that it can learn of concepts, keys, map to values, which are essentially, an understanding of that concept, right? An abstract understanding. So all of this is encoded in the architecture in the form of, tensors, which are essentially a series of numbers. So nothing is, really interpretable to humans, which is what leads to challenges figuring out what these architectures are doing internally, which is why there's a whole field of interpretability and explainability for deep learning models like the transformer and LLMs. But this is the layer of abstraction that these models usually work with. And then once you've got self-attention computed in the multi-head attention layer, and by the way, I didn't touch upon multi-head. The multi-head aspect is basically saying, I'm going to take self-attention and I'm going to apply various different heads, to which are essentially, think of it as multiple cursors within a document, right? So it's looking at various different parts of the input sequence in parallel. So that's another layer of abstraction that this architecture applies. Basically says, I'm going to look at various different positions within the input sequence to create a representation that synthesizes the semantic meaning of that input sequence. So the transform architecture essentially just concatenates the representations that each of these heads generates. It's a simple concatenation operation, but those individual representations are essentially semantic representations that it synthesizes over time, representing different positions in the input sequence, right? So hence multi-head. And then finally, we feed it to an add and norm layer. So we've got, the add part is residual network. So you're adding the input going over to the output. And I know, by the way, there's a lot of technical detail. So if you guys want to go deeper into this architecture and understand things at the next level, I'm happy to chat after the lecture. I've got a primer that goes into a lot of more detail as well. But the thing with these technologies is that every small thing here has essentially a series of papers. For example, the residual connection here, just the simple connection that connects the input over to the add and norm box. That was a paper that came out back in 2018 or so, and there's been a lot of work since then. But the idea is that these kinds of connections help improve training stability, which is why you'll see a lot of these connections taking the input over to the output and doing an add and norm in both the encoder and decoder parts. So those are residual connections, and we add some normalization as well. So that's a norm part, which is a specific type of normalization called layer norm. So that normalizes your input, with standard mean and variance normalization, but at the layer level. And again, we've got a lot of papers, even for normalization, right from batch norm, which normalizes at the batch level, layer norm, which the transformer uses. There's instance norm, group norm, a lot of different options. So, a lot of, ways to, implement a whole lot of these details. And there's, multiple papers for each strategy in the area. But yeah, if you want to go deeper, please let me know. I'm happy to share pointers as well for some of these, blocks. But then once you've got add and norm done, we basically send it to a standard set of feed-forward layers, also called as dense layers. And these are the layers we were used to back in the field. These are the same fully connected layers that architectures prior to the transformer utilized. So this is a standard block, nothing much new here. But again, that has a residual connection as well, which connects the input over to the output and adds that to improve training stability, like we saw earlier, and then that becomes the add and norm. And at the output of the transformer encoder, we've got a synthesized representation of the input, right? In the form of query key and value vectors. So that is the level of abstraction, like I mentioned earlier, the transformer architecture operates at. And the idea behind this output here is that it basically gives the decoder via that connection that connects the left half to the right half a sense of what the input is semantically expressing. So that is the entire essence of the transformer encoder on the left. And once it's encoded the input sequence token by token, the synthesized representation then goes into the decoder, which takes this in as an input in the intermediate layer there, and synthesizes an output token one at a time in an autoregressive way. So to give you an example, say you get started with token number one, right? Basically get started with going from the output to the output probabilities from bottom to top on the transformer decoder, looking at the synthesized representation of the encoder. But what happens is once we have an output token, we feed it back at the input for the transformer decoder to generate the next token. And this cycle repeats one token after another to generate an entire output sequence, whether it's a sentence that you're looking to generate a text output, as in the case of ChatGPT. Well, ChatGPT now also natively generates images as of 2 weeks ago, so that's a recent development. But it generates output sequences in the form of textual tokens, image tokens, and the idea is similar. You feed in the last output that was generated back at the input, so it gives you the next output, and then you recursively go on and on, autoregressively rather, and there you have your output sequence. So this is the entire architecture in terms of how the encoder interacts with the decoder. But we've also got a slide now next that talks about just the right half in a little more detail. So I'm going to touch upon that too. But this is the process going from inputs to the outputs, sampled autoregressively one token at a time.
Explain just briefly about the attention.
Yeah.
What is the name exactly?
Yeah. Yeah. So the transformer encoder only uses self-attention. I touched upon self-attention, but let me give you a quick recap. The idea behind self-attention is that looking at just one input sequence, which is why it's called self. So it's looking at just the inputs, right? Because there's the encoder has no notion of the output that the decoder is generating. It's just feeding in a synthesized representation of the input over to the decoder with a connection in between. It can't see the output. It doesn't know what the output is, what the tokens are being generated one after the other. There is no notion there, right? So it only has access to the input, right? And what it does with the input is it synthesizes the input in the form of query keys and values, which are essentially, think of it as an internal hash map, right? So if there's a concept called if there's, say, the word ship in the input, right, it understands that it's closely related to boat in the sense that both of them exist in the water, and it could be used for water transportation. So that is the hash map that gets internally generated to go from concepts or objects, for example, to what they semantically mean. So those are the keys and values. The queries are the inputs, which help the transformer compare each of the concepts within the input. So that becomes your query, and then it maps it to a key that is most closest to the query. So it does a compatibility check between the query and the key. And then if there, depending on the level of similarity between the input concept, which could be, say, a boat, right, and the key could be a ship, which it has learned from prior data, depending on that compatibility, it accordingly scales the value, which is the notion of what a ship is, applied to the boat based on similarity, right? So there is obviously a good amount of similarity between the two concepts, but they're not exactly the same, right? So that a boat and a ship, right? So that is what attention helps facilitate, figuring out those weights that let you compare one concept against another. So that is the multi-head attention block. Now, the decoder, once we get to the next slide, has another form of attention, which along with self-attention, so I'll be touching upon that as well. But for the encoder, this is how it synthesizes concepts internally, and that's what happens in the multi-head attention. Yes, please.
I'm interested in how this applies to video mining. Because you know that academia literature transform the transcript.
Yes.
But I'm interested to know how industry.
Oh, you mean application in the industry?
In the video mining.
Yeah, we have a lot of applications that are very similar. So, like the recording of this particular call, for example, right? You could feed it into the input of the transformer by tokenizing it. And again, everything goes to tokenization, right? So texts have discrete tokens because we know how to split them. And there are various tokenization methods for text. And we discussed this earlier, but byte pair encoding is pretty common. That's, I think, what the original transformer, actually they use sentence piece, which is internal to Google. But with videos, there are also tokens that need to be generated. So we need to create a vocabulary of tokens. So we have to train a tokenizer first and feed that into the input. And at the output, we can have a synthesized summary of this particular call. For example, we could have the top 5 bullets of what happened in this call and what were the key areas discussed. So we do a lot of transcription and summarization of video calls. So those are very common industrial use cases. So yeah, it's very similar actually. So there's a lot of startups out there in AI that have bots. So maybe you guys use some of these where you could add them to a meeting, as in like add them to the invite list. And essentially what it's doing is once the meeting ends, it gets the video of the meeting or the recording of the meeting, could be audio or video. And those go in as inputs, and something like this architecture, a model like this is able to take it from those inputs to a summary, to key next action items. What was the schedule that was discussed? What is the timeline that we're looking at for some of these next steps? So a lot of the work that we do in the industry, this is, as far as video is concerned, this is a good example centered around meetings. There's also a lot of work in defect detection, for example. So in the factory, there's cameras recording, pieces of equipment being built, for example, right? So how do you understand if, the machines were able to, develop something that's within tolerance of, the physical dimensions or any kind of defects, right? So there's use cases around that as well that take recordings of what's going on in the factory and flows to the machines and interprets that, understands that to just like a human would, inspecting a manufacturing process in the factory and making sure everything's happening within plan. So we've got some of those use cases as well. But
yeah, I have follow-up question. So you mentioned basically compose audio data to transfer and also tokenize the data. And what about the images? If you have video data, basically have to audio data and the image data.
Yeah.
So we just ignore that part. Or
No.
Are there any tools for image data or to combine the information with that the images and audio? So
yeah, we can put both together, and we can tokenize any kind of common modality that us as humans come across. So whether it's speech data, image data, video data, textual data is very common. Everything can be modeled by this architecture or even other architecture. We've got a whole bunch that can state-space models, for example. So we are not limited to audio. There's a whole bunch of architectures that take in images just fine and can return back a summary for you. In fact, ChatGPT can do that right now. So the most recent release generates images, but we've had image understanding where you can feed in an image at the input, for several months now. So yes, we can absolutely have it look at the image portion, the visual portion rather in a video. And yes, we have models, video models that take in the input as the video sequence as the input. So we don't need to segregate the audio channels versus the visual data. With Gemini, for example, you can feed in a recording of this lecture a couple of hours, and it can generate a summary for you just with the input video lecture. So it figures out the audio channels within the input. It looks at the visual modality as well, all of the slides, and it can correlate the two, and it can generate a good summary. So yeah.
Does that then primarily get modified as a customized embedding, or is there
Yes.
convolutional happening in the feed network? Where?
Yeah, that's a good question. So convolutional was and the convolutional networks were the the architecture of choice for the visual modalities for quite some time, starting with I think from the early 1990s. When Jan LeCun came up with the CNN architecture, convolutional neural net architecture. But right now, what we have, we don't have convolutions here to give you a direct answer. But what we have, as far as the transformer architecture applied to the vision side of things, is a vision transformer, which is essentially the same architecture, but like you rightly said, right, the input embedding, that part changes. Because once you got an embedding, a series of, which are essentially a series of floating point numbers, for each token, the architecture is agnostic of the modality. It doesn't care what kind of modality is being fed in. It could be time series data for that matter. So it's able to synthesize, correlations and look at one token with respect to other tokens. So do the relative learning that I was talking about earlier, just as easily with audio, video, any kind of modality. So the input embedding, a lot of that needs to be tailored to the input sequence. And the vision transformer, for example, for when it accepts an image at the input, it actually creates a grid out of that image. So it creates small patches of the original input image. And then it embeds those patches. And those go in as input, right? Which is very different from the tokenization we spoke about for text, right? For example, which is just splitting words into individual tokens. So we make some modifications there, in those layers as the modality changes. But otherwise, the architecture is fairly straightforward. Obviously, you need to train the whole thing on your data, right? We can't just be using the blocks that we have beyond the input embedding trained on, say, a textual use case and then apply the same blocks, for a vision use case and just change the input portion. But you can train this end to end with some modifications at the input, and it can go from one modality to another. And that's been, I want to say, millions to millions. I think is a good number. Millions of papers applying this architecture to all kinds of different modalities across all kinds of different use cases per modality. And we've seen great generalization way beyond text, which is what this was originally, published for back in 2017. So there is, it's a function approximator is how you want to see it. It goes from an input to an output. Doesn't matter what the particular modality is, it can map a function that takes it from input. So it's pretty general in that sense, but yeah.
And I will keep it like the next two things is what is the how does it calculate was it like the based on the number of counts, let's say I want the board as an output. Is what I was thinking.
Yes.
Did it take the number of count of the board in the board or what? How does it calculate the probability that match the semantic over there? And the second question is like, let's say the input is voice, and I wanted to do written comment. I want to output as voice as well. So that's governments are transcript into words and give it as a token. But sometimes when when you try to talk voice chat or back to the beat, and it doesn't take it takes a response, but sometimes it doesn't reply back what you want. So what is the challenge over there and what's happening different?
Okay. I didn't quite get your second question, but let me go with the first one, and then if you can repeat the second one, I'm happy to get into that as well. So the first question, that's a great question, by the way. So a lot of the architectures prior to the transformer, we started with bag of words back in the day, which basically used to model an input sequence of words into a vector that would just be based on statistical counts. So, kind of, related to what you were asking, does a transformer architecture look at counts? We used to do that back in the 1980s and 1990s, where it was mostly count-based and co-occurrence-based, right? How often do you see a word next to another word, right? There's a common saying in NLP, a word is known by the company it keeps. That is the concept that's applied here, right? The co-occurrence statistics, right? Saying, how often do you see, the word boat or ship next to the word water, right? Pretty often, right? Compared to, and all of this is relative. So compared to, say, the word boat or ship next to, say, something, a very different concept, right? Could be, plastic, for example, right? Those are kind of different concept, right? Compared to water, right? So the earlier architectures, right, from bag of words to, we have TF-IDF, term frequency, inverse document frequency, and information retrieval. We've got an upgraded version of that builds upon TF-IDF, which is BM25. All those used to rely on, the earlier architectures was purely count-based, and then we started using co-occurrence statistics in TF-IDF and BM25. But these architectures go way beyond that. They're not just looking at how often a word occurs in conjunction with other words, but it uses that information, yes, but by the way, we do not really have a way to probe into these architectures as easily. So my thinking would be that would be a small part of that whole slice, right? But the other chunks of that slice are going to be centered around semantic meaning, right? Rather than just saying two words occur together at this particular frequency or cadence, it tries to figure out, what the meaning of a particular word is, by basically masking it. When we talk, so bird, for example, is a common encoder, right? So let's take that example where on the left half is, the encoder, right? Like I mentioned earlier. So bird follows that architecture, and what it does is it just masks random words within an input sequence and tries to predict what those masked words would be, right? So that's a concept of masked language modeling, right? Now, think of doing that over, millions of input sequences, right? So at the end of that process, what BERT learns is that, is semantic similarity or semantic notion of what these tokens are and what they mean relative to other tokens in that particular context, right? So this is the entire idea about deep learning. Given enough data, right? And I'm talking millions and tens of millions, and The recent models like Llama 4, for example, that just came out a couple of weeks ago, 30 trillion tokens. So that's a lot of data, and data in all kinds of different, areas, whether it's politics or could be, technology or, all kinds of different verticals and areas. Doing that enough, right, by having it, in case of the encoder, predict these mass words, enables that semantic notion, and the self-attention essentially fuels it to get there. But it does not purely rely on count statistics to answer your question. Those were earlier architecture. This goes way beyond that. We're getting into semantic notion. Count and co-occurrence statistics are pure, do not have any semantic component. This purely statistics where it's saying, the probability of a word being around another word is blah, right? We're not limited to that here. We're way beyond that point. So yeah, that's the first question. Sorry if you could repeat it. Yeah. Yeah. So voice to voice or speech to speech. Yeah. Yeah.
Are trying to do behind the backend work to find out that is the word in different accents. So like sometimes seem to be a different word in the speech. How exactly it knows that it was this word and it is this that time. So what was it they go happening in the word?
Yeah, so there are two methods to enable something of that sort. You can have a model with exactly like this, although we'll talk about the encoder or the decoder in the next slide, and you'll see that it's just the right half, right? Like I mentioned earlier. And in fact, that's the half that is actually used in all of the LLMs right now. We don't even use the left half anymore, and we're able to, with 30 trillion tokens in case of say Llama 4, there's some changes there. We have a mixture of exports architecture with Llama 4, for example, which is a little different than what we have here. And we'll talk about that as well, because we have slides on R1, DeepSeek R1, and that uses an memory architecture too. But barring those few changes, the right half is what we used, and a model like, a model that can go from voice to voice or speech to speech can basically take in inputs, at the very bottom, which are speech tokens. Like I mentioned earlier, you can embed any kind of modality into tokens, and at the output, you'll have speech tokens being generated again, which then are passed through a decoder to convert those tokens into the actual speech signal, right? One frame at a time, and that gets played out back to you. So that is a way to use this architecture, which is what a lot of there are speech-to-speech models that we have now, which are open source. In fact, Moshi is an example from the startup called QTI, which is a real-time speech-to-speech model. So you can talk to it and respond, within 200 milliseconds or so, live, with the architecture on the right actually doing all of that stuff. So if you have speech tokens at the input, and if you model it to have speech tokens at the output, which for the need decoding, you are able to create a speech-to-speech system pretty easily with this thing, and you can have various different accents, like you said, or languages, dialects for each language. All of that gets taken care of as long as you have enough data. The key with deep learning models is you need, data that's well represented, well-rounded. In terms of the data distribution, you've got enough coverage across all of these different dimensions, whether it's accents, like you said, or languages or dialects. We need everything covered. With modalities like speech, we need a lot more data than the text modality, just because speech is a continuous modality, text is discrete. And text is very easily available because we can scrape the web, which is what a lot of the pre-training corpuses use, right? It's data scraped from the web. Speech and video and images are a bit challenging in that aspect. But we've got a ton of these models built already that can span various languages, dialects, and accents. A quick and easy way, to do something similar would you actually use, say, a text-based model, say a Llama, for example, and have another model before the Llama model, which basically just transcribes your speech to text. So you do ASR, automatic speech recognition, which is the task of transcription. Once you got text, you feed it into a decoder, which is text input, text output, and then you can have a TTS model, a text-to-speech model at the output that synthesizes speech from the text that was generated. So many different ways to do that. But if you want low latency, which is usually the case with speech, because you don't want to wait for the whole thing to process, it needs to be real time. Usually less than 200, 300 milliseconds is the requirement for these real-time interactions. So you can go from speech tokens at the input, speech tokens at the output, assuming you have enough data.
So we're actually doing stuff research on this.
Yeah.
You're asking that. They're not as complicated. You break down the audio signal with fundamental audio properties. You can give one of the models released with like a tokenizer for voice. You can actually break it into like a fundamental frequency, acoustic features, and then correlate it with what you know is the actual words in English. You'd be surprised how much it matches. Even though to our ear, we might hear like this, I can understand that. So we break it down to fundamentals and give like a K nearest neighbor, a K search cluster, and when those clusters match the word in English, you can say accent. Probably move on to the code.
Yes, yeah, we've got, we're actually still on the second slide. So this is a decoder. I actually covered most of the, what I wanted to talk about the decoder in the prior slide. So, but thank you so much. Great questions, by the way. So the idea is fairly similar with the decoder. Autoregressive generation of tokens could be any modality like we discussed. And this is what powers a lot of the generative AI models that we see out there. Whether it's Llama, ChatGPT and Claude are closed source and closed weights. But the belief is that this is what's going on behind the scenes with some modifications. This architecture came out in 2017. There's a lot of work done since then. So each of these blocks has received individual attention, and there's been a lot of work that improves upon what the transform architecture originally proposed in 2017. So, and I have a list of some of those papers as well if you want to see what's transpired since 2017. But the architecture is fairly similar in terms of what we use right now. Cool. All right, so that was very quick overview of foundation models, right? And then we're going to get into grounded LLMs, and the core of today's lecture is going to be reasoning models. So I want to get there quickly. But let's talk about grounded LLMs. So the process of grounding is essentially, it means taking a model that's out there, right? An open source, open weight model, and having it work for you, for your particular use case, right? So that is what grounding is. And there are a bunch of techniques that we utilize in the field to be able to ground these models, right? So in context learning, for example, is one such example. And this is probably the most simplistic technique where when you prompt ChatGPT, for example, you can feed it some examples, some demonstrations of what you want the input to be and what you expect the output in that particular scenario to be. And if you do that over a bunch of different samples, which are diverse enough, so the model's learning something new from each sample, for example. Now, we've got models with a huge context window, which basically means they can take in millions of tokens at the input. There's a lot of these models where the input sequence can be huge. Like I mentioned earlier, a video recording of this lecture could be fed into one of these models, right? With so many tokens, with all of this video and audio data going in from the recording. So as part of that context window, we can feed in, tens of samples, hundreds of samples, thousands. We've also experimented with tens of thousands of samples called many short learning as well with some of these large context window models like Gemini, for example. GPT recently announced 3 days ago a 1 million context window as well. So now with ChatGPT, you can, I think it's GPT 4.1, you can feed in, a lot of data, a lot of stuff at the input. Could be a whole book, a couple of books actually, more than a couple of books actually, if you got a million tokens, depending on the size of the book. But that is the idea behind context learning. Give me all of the data at the prompt, and I'm going to utilize some of that and get an answer for you. And as part of the prompt, include some examples of inputs and outputs. That's the in-context learning part, the example, right? So you could give it some demonstrations of sample inputs and outputs corresponding to those sample inputs, which is why it's also called few-shot learning, where you give it some of these examples and it tries to mimic those samples, tries to derive general, trends and, relationships between the input and the output and applies it to a particular test sample that you have for which you want it to predict around. So that is in context learning, very popular, very easy to work with. All you have to do is prompt the model. Right? The other techniques are a lot more involved. RAG is extremely popular as well. And this is the method of choice, retrieval augmented generation RAG. If you want to, if you have a set of documents, could be in various different forms, could be PDFs, HTML pages, text files, any kind of data in any kind of form, which essentially once you convert that form into pure text, the concept of RAG figures out whatever is most relevant from this pool of data that you have available in all of these different forms, and figures out whatever's the most relevant to the question that you're prompting the model with, retrieves that back into the prompt, gives it that information within the prompt after retrieving, and runs the output, runs with the output to get you an output that is grounded in that, information that was retrieved. So RAG is very commonly used to reduce hallucination, for example, because a model now has access to relevant data from your knowledge base, right? So it has that as a reference before it computes response. And I've got slides for each of them, by the way, going into detail. So just trying to give a quick overview, and then we can get into a little bit of detail on the next slides. But RAG is extremely popular in the industry, for example, because a lot of companies and startups, have internal knowledge bases with documents in various forms, and RAG lets them, deploy in a private manner, utilize all of their data, retrieve what's relevant, feed it into an LLM that's hosted on site, and it's able to reference all of that data and generate a response for them. So it's very commonly used if you've got internal data that you want to, have an LLM utilize. Now, this data can be dynamic, so that's one of the big things that distinguishes it from fine tuning. Or if you have data that's changing, there's new documents being added, and there's changes happening, RAG is the way to go. For fine tuning, once you update, fine tuning is the process of updating the model's weights, right, with task specific data that you've got, similar to how RAG functions, right? If you've got private data, we can theoretically use the same data for RAG, use the same data for fine tuning. But the problem with fine tuning is, because you're actually using the data to update and refine the model's weights compared, starting off with a pre-trained model. Once you refine the model further with some of the data that you have, it sticks. And if the data changes tomorrow, you have to undergo fine tuning again, right? So you need to go through the process, as many times as your data changes. But with RAG, it's able to handle this dynamic element in the data pretty easily. So coming to in-context learning, like I mentioned, I'm going to go through this real quick. This is a technique that is pretty simplistic. If you see on the right, I've got a quick diagram that basically says, I'm looking to translate some input from English to French, right? So it's a very simple task. Given English input, I want the translation in French. So what we do in context learning is provide a bunch of input examples, right? For samples that we have data for, or result, or outputs for, and it learns to imitate some of the trends in this particular in these input samples, and then carries it out with a test that or an input that you offer to it, in this case cheese. So this is the idea behind in context learning. Now think about going way beyond English to French, right? You could have a specialized task, which for your particular use case, right? You want to consume an Excel spreadsheet, data in an Excel spreadsheet, and then maybe calculate another set of features or columns in a certain way, reorder some of those columns, and selectively use certain columns to compute certain features, while at the same time using different columns for the other set of different features. So when things get complicated with your particular use case, and you want the model to pick up on some of those details, in-context learning is a great way to share some of that knowledge to the model by showing it certain demonstrations. So you can just, write up maybe a couple of these examples by manually showing the model how it's done, and then give it an example for which you want to generate the output, and it can imitate those examples pretty easily. So that's the idea behind context learning. Now, retrieval augmented generation, or RAG as it's commonly called, like we discussed earlier, this is a technique that is probably the most commonly used right now. If you've got a bunch of input data, in any kind of forms, right? It could be, like I said, PDF files, HTML files, text files. The specific format of the data is that's not the barrier. We're able to convert any kind of file into textual format with various libraries that are out there, open source libraries. And once you've got data, converted or pre-processed from its original form to textual data, the RAG pipeline essentially figures out what's most relevant from that data to the question that you prompted the model with, and retrieves the top K chunks or top K such elements within that data that are relevant to the input that you have or the question that you have to the model, and feeds it back into the prompt, and then has the model generate an output. So that is the entire flow at a top level, which is why it's called retrieval augmented generation. You're retrieving what's most relevant from your knowledge base or the set of documents that you have, and that helps ground the model because then it uses that as a reference to generate itself. So this is a big, the biggest advantage here is that it reduces hallucination. Because think about it, without RAG, you're essentially having the model, explore something while flying blind, right? By giving it a question without any relevant information in the prompt and having it generate an output. But this question might have elements that would be specific to your use case of, say, the kind of projects that are done in a certain lab, for example. We can't expect the model to know, your side of the world, right? So RAG enables that. So yeah, pretty commonly used, especially in industrial settings, please. For RAG? Yes, we do. I don't have a slide on that here, but I have a link to my primer at the end, and I talk about multimodal RAG, and there's multiple ways to deploy a multimodal RAG pipeline. So you can retrieve relevant images, relevant videos. If you have a speech knowledge base, say recordings of meetings or calls, or it can retrieve relevant elements from any kind of modality. So literally it spans all kinds of modalities. Because with RAG, when it looks to find similar elements within your knowledge base, irrespective of whatever modality is in your knowledge base, we just use pure embedding models similar to the ones that we looked at with the transformer encoder. So if you use an image embedding model to calculate embeddings of images, like we touched upon earlier, you can retrieve relevant images pretty easily. Same thing applies to video, same thing applies to audio. So you just need to use, obviously there's engineering behind the scenes to also jot down the type of modality and everything. So we need to bookkeep a lot of that information. But the code change in a pipeline like this, if you want to go multimodal, would just be the embedding mod. So it's pretty easily scalable to all kinds of models. All right, so fine tuning is the other option and the technical term to have a base model work for you for your use cases, domain adaptation. That's what we refer to it in the field and in research. So fine tuning is a method of domain adaptation, as are in context learning, and RAG might not qualify as domain adaptation because we don't change anything with the model. The model is literally the same as what an off-the-shelf Llama or any open source model would be. We're just adding a RAG pipeline, on the side to be able to retrieve relevant bits in the knowledge base. But fine tuning is something a lot more involved as a method, where it adjusts model parameters, within a pre-trained model and off-the-shelf model for a specific downstream task. So that is the entire idea behind fine tuning, saying, hey, I've got a model out there which is open weight, anything that you can find online which is relevant to you, take that model, have it learn some of your own data, right? Some of the data that you have, and then have it carry out a particular task way better than what it could have learned, right? So the issue with fine tuning is, and there's obviously great use cases around it, especially if you want the base model to do something that it has never encountered during training. Could be a new language, for example, could be a brand new task. So all of that is possible. It's just that it requires, high compute and memory, especially, for large models, because you're refining all of the weights within the model. We've got models that are billions of parameters, right? So it needs to be first loaded into GPU memory, and not just the model, even the data that it's being used for fine tuning, that also needs to be accommodated in the same GPU memory, right? So you need to have enough GPU VRAM, which is GPU memory, to be able to accommodate the whole model. And then you begin the process of fine tuning. So there is a bit of an overhead there. Full fine tuning is basically a variant of fine tuning that modifies all of the layers or weights within the model. So we don't selectively choose which particular weights that would be relevant to this particular task would undergo an update as part of the fine tuning process. And it's called full fine tuning. But this is cumbersome because you're trying to modify the entire model. We have huge models right now. So there are variants of fine tuning. We've got surgical fine tuning. The full fine tuning illustration is on the top, on the right, and which is, like I said, given a label training set, give it to a pre-trained model, and it updates all the layers. Right? Now, there are variants, like I said earlier. Surgical fine tuning is one of them, where it figures out which layer within the architecture is most relevant to your task, given how different the task is compared to what the model has encountered during training. So the magnitude of that difference is a big part of what helps us decide, which layer within the model would be relevant, right? The earlier layers we've seen tend to focus on, general features. So if you've got, in this case, the figure from the paper here, and I've linked the papers here, and I think we already shared the slides. So if you want to go deeper, feel free to take a look. But in this particular paper, they looked at vision use cases. So the input was image data, and the output was, I believe in this case, figuring out one of the, a couple of hundred categories of what the input image is, right? So depending on what your, the label training set that you have right now with you, the data that you have available, depending on how much that is different from the data that the model was originally trained on, we accordingly choose a layer. So that is the idea behind surgical fine tuning. And this one, this is yet another variant of fine tuning, and this is what is very commonly used in the field, because this tackles the problem of not needing to fine tune the entire model or even choosing a specific layer. So it makes the process very easy and modifies only a small fraction of the parameters. So it's called parameter efficient fine tuning for that reason. And there are a bunch of techniques. I've got a primer on it, link later in the talk. There is one technique that is very commonly used in the field. It's called low rank adaptation, LoRa, and that's the diagram on the right from the LoRa paper. And the idea is that it uses low rank matrices A and B. The orange matrices on the right does not touch the main weights of the model on the left, the blue box. That remains untouched. It's frozen. So it does not change anything in the main model weights, learns two sets of matrices, A and B, low rank, and then finally adds the product of A and B over to the pre-trained weights at runtime, depending on what it is that you're looking to have the model do. So you could have the model go from being specialized to one task, one thing that you want the model to do, by just by having a specific A and B set of the weights within the A and B matrices that are learned, and then swap it at runtime to a different matrix if you want the model to do something else, right? By having another set of matrices learned. We call it adapter swapping. Apple, for example, has a white paper on some of the Apple intelligence features that powers a lot of the Macs and new iPhones. They use a whole lot of this behind the scenes. So if you want to, say, modify an email to suit a particular style, they have an adapter for that. A LoRa adapter is what it's called. So there's a LoRa adapter for that gets utilized behind the scenes. But if you want the same model to maybe summarize a web page for you, right? So you just swap the adapter at runtime, with something that was trained earlier, and it can now summarize with the same base model. So the base models remain static, and you just swap the adapters.
How different is this from the mixture of experts?
Yes. Mixture of experts is a very different paradigm, and we have I touch upon it in DeepSeek R1, so I'll talk about that. In the sense that this lets you do multiple tasks depending on which set of matrices, low rank matrices, the orange matrices A and B that you use. You can do multiple tasks with it. Mixture of experts is used during training. So you can pre-train with the architecture. This comes after. This is fine-tuning. So it's assuming that we have a model. Mixture of experts would be part of the blue block in this case, which is the pre-trained weights. So I'll touch upon that when we get to D3 R1.
Do you ever retrain the embedding?
No need to retrain embeddings unless you're looking to do something very different with the model, which because there's a model for most use cases, right? So if the base model is already aligned with your modality, for example, so say it consumes vision or speech or text, that forms your blue block, right? So that's the pre-trained weights. And A and B do not change anything with the embedding. They just change some particular weights within the blue block by adding doing an addition, right, of the product of A and B. So effectively, the pre-trained weights remain frozen. So you're not changing anything, let alone the embedding, nothing in the.
Is this only on decoding?
Yes, this is the decoding. Yeah, so this is at inference or runtime as you're decoding with the model. All right. So I've got a quick comparison of all three in context learning, RAG, and fine-tuning, which is what we just discussed, right? All three techniques. So I'm just going to go over it real quick before we get into the part of the lecture, which is reasoning. So knowledge updates, like I said, in context learning, you're not changing weights. RAG, you're also not changing weights because it's external retrieval, but with fine-tuning, you have to, it's more involved. You need to start modifying weights depending on what, to reflect some of the nuances of the data that you're looking to have the model master. There's external knowledge in RAG, for example, that is being retrieved, but within context, you just supply some of these demonstrations within the prompt. And fine-tuning is basically static. You take that knowledge, fine-tune the model, and then it's learned, some of that data. It could be facts, for example. I know in our lab, we were looking to have, Llama understand some of the history behind SDSU and, the center in particular. We went through fine-tuning because that's a good way to have the model memorize some of, this data.
We also use fine-tuning with generic model.
Yeah.
We want to give it a little bit of a more functionality rather than constantly talk about a check, especially if you like an instruct model.
Yes. Yeah, so go ahead, please.
As you said, that RAG is one of the most popular methods in the industry nowadays, and a lot of Korean companies in Korea, they're interested in applying the RAG into their company environment.
Yeah.
And they found that there is a major challenges in using the RAG because of, as you said, exactly matching the context from the our information is very difficult. Usually they use the vector database, but it's only a kind of a counting the word by word, so it's not really the context matching. So some people kind of predict that the RAG is not as bright as we expected. What do you think is the perspective of RAG?
Yeah, that's a good question. So RAG, the success of a technique like RAG depends on some of these micro decisions that you make at every step, right? And probably the biggest decision, the decision as you set up a RAG pipeline that would apply in your case where you mentioned that retrieving relevant context might not be as easy. And, so chunking, for example, is a technique or concept within RAG that figures out what granularity to slice the input data at, right? So for example, think of a book, right? A book has book chapters. Each chapter has multiple sections, and then each section has multiple subsections, and further on, right? What level of granularity do you chunk at? Because these embedding models, we've got long context, long form input embedding models to where they can take in a whole chapter at a time, depending on how long a chapter is, or, but we've got, 8 to 16 to even 32,000 input tokens with embedding models. But the challenge is if you embed a whole lot of data, so if the unit that the level or the granularity that you're operating at is is, a big data chunk, which could be, say, a full chapter. The problem is the embedding doesn't exhibit strong fidelity at runtime, right? So when you retrieve, the embedding is only going to capture what what the model thought was most relevant in the whole chapter, right? And encode it in within, for BERT, for example, it's 768. That's the embedding set. So it's 768 floating point numbers. A chapter could, like in a big, well-written book, could be, huge, right? And embedding all of that information in 768 tokens might probably not be the best bet, right? So what we have in RAG are methods to figure out what level of granularity do we use, what do we chunk, or do we calculate these embeddings for? And these embeddings are the ones that I use for retrieval or similarity search at runtime, right? So say if you embed only small paragraphs with, say, 2 or 3 sentences, obviously that the embeddings are going to be richer and, higher quality compared to embedding a whole chapter, because then you're having the model look at much less data and encode nuances of just, say, 3 or 4 lines, say if it's a very small paragraph. So it does a better job there, right, compared to, say, embedding the whole chapter or, a couple of sections within a chapter. So depends on what chunking method was used, what granularity was used to chunk that data, and what embedding models were used. There are different types of embedding models for different kinds of data. The models that are specialized for legal use cases, for example. So if you use the right embedding model, it's going to capture some of the most important notions because it understands legal use cases better than medical use cases, right? So a lot of these micro decisions need to be thought through well. It's a whole science. RAG has thousands, tens thousands to hundreds of thousands of papers out there. So there's a lot of analysis done over all of these small components, small decisions. Even for chunking, we've got tens of different options right now. So embedding models, there's so many different options available. So all of these decisions have to be made right picks and choices have to be done to be able to improve the efficacy of that.
I think that is the best way.
Yeah, depends on the input data. There's no one size fits all, right? The thing with RAG is that, if you assume, that your data is never going to change, fine tuning can get you a little bit of a better performance because you're actually having the model learn some of that data. But in a lot of use cases, it's a tough assumption to make. Can we say that we are never going to have to change, an important piece of data? If you don't want to make that assumption, then RAG is better because you're not changing the model. So, and just retrieving relevant context externally, so it works better, which is why the industry and like say, if you're deploying a RAG pipeline for a chatbot for the, department or for the center, right? As we have more projects, happening in the center, RAG would make more sense, right? Because the model can stay up to date. If you fine tune a model with a lot of that information, problem is it can't automatically learn about new events and new happenings since you fine tune the model.
We've done a lot of RAG and working organizations to do. There's a ton of so-called best practices and things that work terribly on your data. There's just no way around experimenting, setting up your database, even like the vector database that you choose matters.
Yep.
The batch size, the chunk size, the embedding model, even the model that's retrieving from the LLM side. There's about 20 variables. There's no way around just experimenting until you get good results. Sometimes we use like supposedly the best for setting, terrible results. And then we just spend days, sometimes weeks, tweaking one setting, evaluating, looking at our retrieval, especially building a search engine. Like you have Google, which is generic, or you have like law databases or law searching. So this is very squarely MIS. Like I think RAG in terms of like the database, the vector, the embedding, the encoding, the retrieval, the TD idea, all that stuff is like square in RAG. And then there's re-ranking, taking the results and then sorting them by most, because you could get a bunch of results, but then you have a needle in a haystack. So there's just so many steps to it.
Yeah.
And it's all brand new. You kind of just dig in. It's terrible.
Yeah, a lot of nuances in the entire RAG pipeline, right? A lot of these micro decisions that have to be made. And like Aaron said, right, it's empirical science, a lot of this. So you have to have a test set. examples that you have some expected outputs for, and then tweak each of these parameters, to figure out what gives you the best performance on your test set. And this test set is something that the model should have, or the pipeline should have never seen. So you optimize the pipeline based on unseen data. So that's how we set up a lot of these. All right, with that, we're going to get into reasoning models. And just want to do a time check. So we're at 11:20. Yeah, I'm going to resume, but if you let me know if we've got like 5 or 10 minutes, and then I can maybe expedite a bit towards the end. But there's a lot of nuances here. So I put together a bunch of slides, and we're obviously going to be sharing this offline too, and you guys are free to reach out if you have any questions. But I'm going to try to cover as much as I can. So reasoning models, and the reason why I wanted to spend more time on this is because DeepSeek R1 came out late January, and it's picked up a lot of good traction for a lot of good reasons. And let's figure out why. So if you look at the figure on the right, this is from the DeepSeek R1 paper. So this is a good, canonical or poster child example of why reasoning models, are, the model of choice, the method of choice for, mathematical reasoning or coding use cases. So in this case, the user prompted the model with a mathematical question, and the DeepSeek R1, basically started thinking about how it wants to solve that question, exploring various different paths, one after the other, and figuring out what makes sense to pursue in what's the best strategy to go ahead with it for a question, mathematical question like this. Now, so you'll see the think tag up there in the response, right? So this is all part of that reasoning. The whole snippet here in the response is part of that reasoning. And we call this long chain of thought reasoning. The model is dumping its internal thought process and telling us what it thinks, are various strategies to go ahead and exploring one strategy at a time. And in the middle of exploring a particular strategy, it actually realizes that a certain strategy isn't quite panning out well. So it actually starts saying, wait, there's an aha moment that I can flag here. And it starts looking at things with a different lens beyond that point. So it starts reevaluating the strategy up until that point, step by step, to figure out if this is indeed doable, or should it switch ways to a different strategy altogether. So this is a good example of what a reasoning model is great at, which is given a problem statement like a mathematical question here, or a coding use case is pretty common as well, where there are multiple ways to go ahead and answer a particular question in a lot of these scenarios, right? There's various implementations for a coding problem, for example, right? What to use when, and what are strategies that make sense in this context versus what would be better in a different context. It starts to evaluate all of those. So the DeepSeek R1 paper called it the aha moment, which has been pretty talked about online, and that really drew a lot of good attention to DeepSeek R1. And with DeepSeek R1 will touch upon some of the different specifics about how we got there. There's a process which is a little different, way different than what we're used to for non-reasoning models. So in terms of getting here to this point, it took DeepSeek AI, the company behind DeepSeek, a bunch of different methods and types of algorithms and ideas to get here. We'll touch upon that. But this was the figure in the paper that got people talking in late January, and this led to a lot of attention around reasoning models. Something that we don't see with pure general purpose foundation models like prior Llama releases. There's a Llama 4 release upcoming for reasoning as well. But up until this point, with regular general purpose models, we don't see them evaluating various different options and strategies for a problem statement, just like humans would, right? When we're given a problem, an analytical problem that requires us to look at various different paths, we're seeing some of that coming up in reasoning models as far as their internal thinking goes. So why did we not see this earlier? Why do traditional LLMs struggle with reasoning? So with the decoder architecture that we looked at earlier, which is what powers a lot of the traditional LLMs, and a good part of that carries over to reasoning models too. They're not fundamentally different in terms of the architecture. We're still using the transformer architecture, but with a mixture of experts like we chatted about earlier. So we'll have, I'll have a diagram on an upcoming slide that talks about the MOE mixture of experts architecture too. But fundamentally, they are very similar in terms of how the architecture is laid out. But how they are trained is a different story, which we'll also touch upon. But the traditional LLMs were great at autoregressive next token prediction, which is what we spoke about earlier. They do a lot of good pattern recognition, but they don't factor in any correctness within that pattern recognition. Or generally, when we train these models, there's no reward or no correct notion of correctness that we offer to the model beyond the data that they are trained or fine-tuned on. And the other thing is that with DeepSeek R1, as we'll see, they factored in correctness by having rule-based rewards during RL reinforcement learning training, where say for example for mathematical use cases like the one on the prior slide, the mathematical question, or coding use cases, because it's easy to come up with tests or checks and balances as it's trying to get to going from a question to an answer. It's going through all of these various steps in between. That valuation in between, right? That validation in between that lets you check for correctness via rule-based rewards, which we'll also talk about in detail. That is what made R1 figure out what the best strategy is given the question. So that is where it developed, a lot of its reasoning, and it was, there's two variants to R1, DeepSeek R1.0 and just DeepSeek R1. R1.0 was trained with just RL, and it developed most of a good part of the reasoning. In fact, the example that we saw on the last slide where it goes to the aha moment is from R1.0, which is just one stage of R1 on top of the pre-trained base model, which is DeepSeek V3 is what they use, the prior model that they had already announced. So they just took that off-the-shelf model, applied RL to it, and then you see these aha moments where it's able to figure out if it's going down the right path or not. So this is the slide on R1 on the right. We've got the MOE architecture up top. So the dotted box on the right at the top is the MOE architecture. So you'll see that, which is a magnification of the feed-forward network on the left, right. So with an MOE architecture, what we usually do is the feed-forward layers, which we also had in the transformer overview slide. These are the same layers, by the way, on the left. In fact, it clearly says transformer block. So this is the transformer architecture overall, but the only thing that's changed is, the MOE part and also the multi-head latent attention as well, which is the dotted box on the bottom. So let's touch upon each one of these boxes on the right. I can give you an idea of what's an MOE and how, it's useful in this case. And Llama 4, which was announced a couple of weeks ago, also uses an MOE architecture. They've shifted from a pure dense architecture, which is what we were used to with, plain old transformers back in the day. Now we're shifting gears towards MOE architectures, and it looks like the trend is going to continue with other models as well. The MOE architecture basically lets you map the feed-forward network into multiple different, individual specialized experts. So instead of having, one layer there, we essentially have a bunch of, or a couple of layers is what I think the transformer architecture, original architecture used 2 feed-forward layers within the feed-forward network. Here, we basically have much smaller blocks. These are all dense blocks themselves. When you go from 1 to n, right, in that diagram, right, each of those small boxes, squares, are specialized experts, which are initialized randomly and trained during runtime to be specialized in certain areas, depending on the input token. So depending on what token it is processing at the input, it selects a particular expert from one of these n options. Now, the implementation that we use here actually selects multiple experts. So, and that is configurable. So Llama 4, I believe, selects one expert out of, 128, for example, for Llama 4 Scout. Now, in this particular case, I forget how many experts were chosen, but that's a configurable hyperparameter or configurable parameter during training, where you basically figure out how many experts you want to consult for depending on that particular token to proceed with a representation at the output of this particular block, right? So it only figures out, with a router before these exports. So you'll see a router block right below the 1, 2, n squares. And the role of the router is essentially, given the input representation from the prior layer, it figures out what are the most relevant k exports, where k is a parameter to be chosen, usually set to 2 or 3 or somewhere in that number. Somewhere in that ballpark, it selects relevant exports. So router gives you a distribution. So you'll see a little distribution to the right of the router block, which basically is a probability distribution. So it tells you which expert is going to be, the most likely to offer you, a better output here, given what we have at the input. And it selects the top k experts based on the probability distribution. So the highest k numbers within that distribution, the probability numbers get chosen. And accordingly, those experts are what are used to pass output onto the next layer. So this is what makes an MOE architecture. So this is only done for the feed-forward part of the transformer architecture. Now, the attention layers, and the part on the left, by the way, the transformer block is exactly what we saw in the initial slides when we started off the talk. So, essentially now, instead of the feed-forward network, we've got the MOE part. Instead of the attention block, which we talked about earlier, the self-attention block, the multi-head self-attention block, we've got a different variant of attention here, which is a multi-head latent attention. So this was it. By the way, these innovations were introduced in DeepSeek V2 back in the day. And R1 actually utilizes these with some minor modifications. Actually a DeepSeek V3 also came in between, which came out in between V2 and R1. And that utilized this as well, along with some more further changes. And R1 took that further and added a few more changes. But this was originally proposed in V2. I've linked the paper down as well in the caption. But coming to MLA, multi-head latent attention, which is a more optimized version of the traditional attention mechanism. What we do here is that the key values that we talked about earlier, we create a compressed representation of them, and essentially with a very similar technique as low rank adaptation, the low rank part of low rank adaptation. So you're decomposing the matrix into the key value matrices into smaller matrices, achieving a 93% reduction in storage for the key value indices, which are essentially the weights that we're learning. And that reduces the amount of VRAM that is needed to run some of these models significantly, because the key value matrices are essentially the heart of the attention architecture, like we discussed earlier. And if you bring those down in terms of size, obviously you can house a much bigger model now because it's compressed down, and get it into your GPU VRAM much easier. So those were the two biggest innovations in V2. Now, with R1, it also uses multi-token prediction, which is the fourth bullet point that I have here on the slide. The idea is that it predicts multiple tokens per time step rather than one token. Earlier, we spoke about the autoregressive generation of the transformer decoder architecture, which is one token at a time, but they actually use multi-token prediction, which is a technique that similar to a technique put out by Meta a couple of years, last year actually. But they've adopted that as well. And the last bullet point I have here on the slide talks about the precision levels. A lot of the computation within the architecture is done with 8-bit floating point numbers instead of 32 or 16 bits. So those are some of the key changes in R1.
That why NVIDIA stock.
Yeah, the biggest reason was that R1 was trained on a very limited compute budget. I forget the exact. Yeah, compared, a lot of the big labs don't reveal their numbers, so we don't know what the reference point is, but they were able to get all of this done, and a lot of these great out-of-the-box optimizations, like the MLA part, right, multi-layered attention, which reduces VRAM requirements significantly, and then delivers good performance at the end of the day. So if you got, the efficiency is pretty high, right? Very little input and great output. So that was a big reason behind the stock tanking. Yes, please.
Two questions.
Yes.
For the mixture experts, are these experts explainable? For example, do we know that the first one is good for math and the second one is good for translation?
Yeah, that's a great question. There's a paper by a different company called Mistral, and they have a model called Mixtral, M-I-X-Tral, so which is a mixture of experts architecture. And this came out a couple of years ago. And they did something called as an expert specialization study. So they trained a MOE model, mixture of experts model themselves. And once the model was trained, and by the way, all of these blocks are initialized randomly. So everything is being trained as part of the training process, right from the router to what the specific experts are experts at. All of this is trained as part of the process, right? As part of the training process. But what Mixtral did was it took a model that was trained by them. So they had an MOE model. And they then did a study feeding in tokens, and looking at characterizing or profiling which experts were being triggered. So we did see a specialization happening depending on the topic and depending on the token. For different topics, so for example, for politics, there was a set of experts that were being triggered. Compared to science and technology, it was different, and compared to say geography, it was different. So there's some great plots in the paper too happy to share. But we've seen some specialization happening amongst experts as these are being trained.
Second question, more interested in the multi-token prediction. So my assumption was still using the auto-regressive approach, but
Yes.
each time we get multiple.
Yeah. Yes, still autoregressive, but there's multiple heads at the head is essentially a layer at the very end that lets you sample, comes up with the probability distribution for the particular token that you're sampling across the entire vocabulary, right? So it tells you which token has the highest probability of occurring at this time step. Now think of multiple of those heads.
But it's a conditional.
It is conditional.
Because the second one has to be based on the
Yes,
first one.
that's absolutely correct. So it basically, based on the highest probability of a token at one time step, that gets fed in as input to the other. And then when we sample, there's a lot of sampling methods to a lot of different work in the field in terms of how to best sample the output too. So, but what typically is used in a lot of these models is greedy sampling, which is essentially taking the highest probability token at the output. So that is the next token or the token after, everything is conditioned on the highest probability token from the prior time step when you're generating multiple tokens at a time. All right. So this slide actually talks about how DeepSeek R1 was trained. Like I said, the architecture, we just covered that on the prior slide, right? So there were two big changes, the MOE and the multi-head latent attention. Now, as far as the architecture is concerned, those were the two biggest changes. Otherwise, it's a regular transformer decoder. Now, here, this slide basically tells you how we utilize that architecture and went from a non-reasoning model at the input, which was DeepSeek V3 is what they use as the base model, their prior model, took that to DeepSeek R1, which while invoking reasoning within R1. So this is a reasoning model right now, which I showed you a couple of samples from, which can think through different strategies and have aha moments. And so there were 4 stages involved in training DeepSeek R1. The first one was just supervised fine-tuning. We covered fine-tuning earlier, so it's the same strategy, but not the parameter efficient variant. This is just pure full fine-tuning, where they took V3, DeepSeek V3, and they fine-tuned it with long chain of thought traces, similar to the example that we saw, the mathematical example, right? So those were the chain of thought traces where it thinks through the problem. So that is where stage 1, we spent time in stage 1 trying to, get the model to understand that it needs to think through problems, right? There were about, I believe, 600,000 samples or so that the model was trained on. So the input question and the chain of thought trace that shows it how to think through the problem, just like you teach a student, for example, and then the final output. So that was stage one. Stage two, it was reinforcement learning. This is where DeepSeek R1 utilized something called as GRPO, Group Relative Policy Optimization, which is, I've got a slide coming which talks about GRPO in detail, including the equation that powers GRPO. So this is an RL technique. This tells the model that, given an input, right, it basically lets the model sample, n number of outputs by changing internal parameters like temperature, which is a hyperparameter. So it generates a bunch of different outputs for the same input, same prompt. And it with reward functions, which we've coded by hand, DeepSeek R1 uses rule-based rewards, right? So we code up, it's just like a grader would, right? For when we're grading, student answer papers, right? There's rubric or there's criteria that you for each question, right? So it's the same thing here where we're basically coding up rule-based, rewards to figure out what is acceptable versus what is not, or what is mildly acceptable. So there's a range of 0 to 1, for example, for different kinds of criteria. And based on responses that get DeepSeek R1 the best reward, those are the ones that are, that we positively reinforce with the model, and accordingly, the examples that we that give us lesser rewards are the ones that we do not want to reinforce with the model, right? So this is the step that tells the model what to do more of versus what to do less of, right, in its output. So that's GRPO, which is the RL technique, which we'll cover in the next slide. And then the other stages are relatively lightweight. The next one's rejection sampling, expanded SFT. Basically figures out the top RL outputs that we want to reinforce further. So it's a little bit more of what we did in the last stage, but combined with some expanded SFT as well, where we did more supervised fine-tuning on non-reasoning tasks, because we want DeepSeek R1 to also be good at things beyond reasoning. We wanted to have conversations with users too, right, about other topics and be able to have a conversational bridge. So that is what the other two stages focused on, things beyond reasoning tasks. And the final RL phase is also very similar, like I said, is tailored towards non-reasoning tasks, like say multi-turn funnel. So these were the 4 stages. And then I've got a detailed slide that talks about GRPO. So this is what powers DeepSeek R1. We've got a nice equation on the right. And this is from my primer on DeepSeek R1, which breaks down each component of that equation. And there's a lot of detail here, but I'm going to try my best to give you guys an overview, but let me know if you need more detail, if you have any questions. But the idea here is plain and simple. What GRPO says is it actually builds upon a similar technique called PPO, proximal policy optimization, which OpenAI introduced, and that is this was proposed in a different paper called Instruct GPT back in the day. And this was a big reason behind the huge ChatGPT moment we had back in December of 2021 or 2022, which started the generative AI wave in a lot of ways, because the responses started to feel a lot more human and a lot more helpful, for example. But 5 minutes, okay. So GRPO built upon PPO, and the idea is that we calculate rewards for each of the different responses that we sample from the model. And with this equation, we figure out, what the particular objective is that we are looking to maximize. So this equation is what is maximized as part of an optimization process. There's a bunch of different terms, like a penalty term, KL divergent term, to reduce the amount of variation we see the model, the policy is going through at each step, because we don't want the model to start being drastically different than what it is currently at, right? So there's stability constraints as well as part of this process. RL is a technique that is very difficult to tame compared to, say, supervised fine-tuning, in the sense that the RL process tends to be unstable unless you take special care. So a lot of the terms in this equation are tailored towards making sure there's stability in the process by ensuring the model doesn't diverge too much at every step, but takes step-by-step changes as it gets to its final point. So that is GRPO at a top level. like I said, happy to go over it offline if you guys have questions. A lot of different terms here. This slide isn't quite as important, but I wanted to, had we had more time, I would have loved to go over other variants of policy optimization. There's also DPO, for example, which was, that is what most of the other models that have revolutionized the field, like including a lot of the Llama models, for example. Since the early versions, since Llama 2, I believe, everything's used DPO in the field. So that's direct preference optimization. DPO we talked about earlier, which was by OpenAI, which led to the ChatGPT moment early on, and GRPO is what DeepSeek R1 uses. A lot of different variants. There's actually hundreds of different policy optimization algorithms as well, but these are the top 3 most common. Reinforcement fine-tuning is, another method which basically is, this is actually something that I would recommend for a lot of the projects. And if you guys are looking to, if you don't have a whole lot of label data, but want to leverage an off-the-shelf model and have it reason about in scenarios beyond math and coding, say for a technical use case or something associated with the project in your lab, reinforcement fine-tuning, RFT, is a great technique because it basically leverages all the good bits about RL that we looked at, including reward signals, but doesn't need as much label data compared to supervised fine-tuning, which you saw earlier. So there's a case study, I've linked it there, where with less than 100 samples, we are able to have the model learn how to do a new task very easily, a code transpiling task, which is the task of converting code from one language to another, just less than 100 samples. So yeah, the RFT is, this just came up a couple of months ago, actually after DeepSeek R1, so probably early last month or so. And it's been creating waves as well, reinforcement fine-tuning compared to supervised fine-tuning, which we were used to earlier. All right, so I've got a couple of more slides. I've included some application areas here. These are technical. These are areas where we can apply RFT, like I was mentioning earlier. So if there's, we can, obviously use the full-blown RL stack as well, which DeepSeek use, but like I said, RFT really simplifies the flow. So if you can implement, checks in code, right? Something that tells the model, gives the model a reward signal to tell it that, this output, this particular nuance about this output was great, and grade the output on various different dimensions and create a lot of these reward functions, which are basic Python functions that just grade the output on a scale of 0 to 1. And then you just accumulate that reward. That's enough signal for the model to learn with a framework like RFT. So then there's in fact no deep learning or no RL, use as part of just creating these reward functions, because they're simple Python functions that take in an input, check for certain patterns, could be certain usage of certain words, or if it's code, we can actually compile the code, run the code, check for output. If you're able to objectively or automatically verify certain traits of the output, then RFT is a great option, because then you don't need as much data, just with less than, even 100 samples like we saw on the last slide. You can implement it for, hypothesis testing or for tutoring, for example, in education as a TA, for example, for your class. Speech generation is another one. If you can grade the quality of speech output with a rule-based function. Robotics is another one. A lot of different use cases, but the essence is that the output has to be automatically verifiable with a simple Python function. So you need verification power. You don't need generation power. You just need to have the ability to verify. And like I said, those can just be regular Python functions. There's no deep learning, no RL, nothing in those functions. Just given an input, tell me a score, give me a score of 0 to 1. That's it. Non-technical application areas, creative writing, for example. And by the way, you can have another LLM also judge the output of the model that you're training. So you can get creative with these rewards as well, where you can have a different model set up to grade the output of the model that you're looking to develop. As long as you can give a reward signal, that's good enough. But whether it's creative writing, legal document analysis, travel planning, interior design, mental health support. We've done some work there on the mental health side as well as part of the center. But these are some non-technical application areas where, again, the essence is if you can verify the output in any way, you can use RFT to have a free and open source off the shelf model do a task for you way better than it can. And then lastly, I've got some pointers. These are some links to papers, like I mentioned earlier, for a lot of the different areas within the transformer architecture, for grounding LLMs, and for reasoning LLMs. This is a very small list. I've got a much larger list on my primers. So I've got primers on transformers, RAG, DeepSeek R1. So for RAG, for example, we discussed a whole lot of those different design decisions that you need to make. I have a whole lot of analysis around these design decisions and what makes sense where. DeepSeek R1 we covered. We've got primers on RFT as well. PEFT is the LoRa technique and a bunch of other techniques along with LoRa. And preference optimization, we looked at GRPU and TPU and PPU, and there are, I've covered, I think, 10 other options, but there are hundreds of other options right down the field. There's so many papers. The momentum in this field is insane. So a lot of movement. Yeah, with that, this brings us to the end. Yeah. Any quick questions? No. Yeah, that's a good question. So if you look at OpenAI's model offerings, right? We've got O3 that was recently announced. The reason why there isn't one model that's offered by even like Anthropic has Claude Thinking, for example, Gemini also has a thinking variant. Then all of these providers aren't offering one model, right? And the reason is because these reasoning models are great at mathematical scenarios, coding scenarios, and a whole lot of other fields which will open up soon. Like I said, as long as you can do verification of the output in some way, you can use a reasoning model and fine tune it for your use case with very little data. But when it comes to creative writing and say even summarization, a lot of those general language generation use cases, we don't see reasoning models to be doing great at. And that's just because this is the first iteration of reasoning models. We will have models that are going to be great at literally everything. And we're seeing some internal leaks and a whole lot of these labs working on, incorporating maybe a router in the front, which is going to, figure out if you need to do reasoning for a question or not. Right now, reasoning models sometimes do reasoning for basic questions too, which isn't ideal. Like us as humans, it would come to us naturally, a simple question, but reasoning models tend to reason for a lot of cases where they shouldn't be reasoning. So a lot of that is being refined too. But in the future, I think there's going to be, in the near future, in a couple of months, maybe given the pace of AI research, there's going to be like a router in the front, which figures out if you need to reason for a question like this or not. And that can also invoke a different model, say if something better than, say, creative writing or, say, a legal use case. So that will route queries accordingly. But at this point, given that we're very early on in the research of reasoning models, they're not good at everything else. So we've got a bifurcated flow depending on what you're looking. Yes. Sure. It's a good question. It is there is a lot of work happening in carbon footprint emission. So when you train these models, what is the impact on the environment? There is a separate research field, a lot of work being done there. At this point, I think the field is doubling down on making sure that we see a good level of performance on these models first. And a lot of this is afterthought at this point, but there is a separate research field, a lot of work being done there as well to understand what the impact is of training some of these models. I think there was a question. Yeah. 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 Yeah.
So is it ever going to be a time where it will switch models and give me the simplest solution? It's going to reduce the cost for them and reduce the time for them.
Yeah. That, like I said, right, I think there's going to be some sort of a router that will come in earlier in the pipeline, right? So once you feed in the query, it's the router, the job of the router is going to figure out the best next step, right? Do we need to think about this question? Do we need to invoke a reasoning model at all? Do we just use a general purpose model? In fact, it could be much more nuanced, right? You could think of figuring out if a small model, say a 1 billion parameter model, is that good enough for a task like this? Can I give a decently, good response versus say 8 billion parameter model or a behemoth level of a model or 2 trillion parameter model? So I think there's going to be a lot of nuance to that, but I do see this being one of the next steps in the field. I think OpenAI has already expressed that Sam Altman tweeted that he doesn't appreciate the model, the model selector drop down, because that's additional work for the user to figure out what model to use. It's going in the near future, in maybe in the next couple of months, we're just going to see, one interface. You ask it a question, it figures out what's the best for you, unless you do want to override, with a manual option. Right.
Regarding the context window.
Yeah.
Like LLMs or like AI models have such big volume, right? Especially big context windows.
What specific problem?
Well, why is so the picture how like I know that for example Gemini has no content, but why is it regulated to a specific amount? Why can it just
Have infinite context?
kind of
That's a good question. It's mostly centered around training costs, and I think ties in very well with some of the impacts of training these models. So the main attention mechanism, the traditional mechanism that we looked at earlier, and there's been some innovation there. So we have a lot of follow-up works that have refined attention, like the one we saw with DeepSeek R1 is the latent attention version. But the main attention mechanism was quadratic in nature. I mean, it still is, but there's been linear implementations of attention. There's been latent implementations. But the challenge is training models becomes way more, it scales quadratically the cost. So what we do is we don't typically train models with a large context window off the bat. We train it with a small context window and then perform context length extension, which is a separate step after, rather than just directly training it with millions of tokens, because that would require, it scales up the compute cost and requirements exponentially. So yeah, that's not as effective, but we have 10 million tokens with Gemini already being experimented in research. So, I mean, it's already almost there right at the door, and in the next couple of months, there should be a whole lot of these models. I mean, Llama is already at a million tokens now. Gemini's had million for a while, and like I said, 10 million research. So you can feed it a lot of information.
I have a question about mixture of experts.
Yes.
Where that's going. Sometimes I think it's cool, but then at the other hand, you have a model like Maverick, which is on the floor, which has like 400 billion.
Yeah.
But then you're getting that number somehow, which you're getting that. But then you're only using like 17 billion of it. It almost makes me like, well, like, are we using the rest of it?
Yeah.
Is there like a technique like we do with random forest where we could like use all of them and combine them, average them down, reduce variance? I mean, is there anything like that, or is just 17 billion enough specialized versus like what if we use all 100 billion?
I've had that idea for a while. Figure out what experts you're most likely going to read, and just like operating systems do caching of, within memory, right? So you could, have some of the most common experts and even predict, a little in the future based on the input tokens, looking at the input tokens, which experts you'll need. Have those in memory, have the others being paged. A lot of the current architecture actually does paging. VLLM actually has an implementation internally. But the scale, like you said, right, is drastically different, right? The amount of active parameters, that's a very small fraction of the total parameter count, especially with Maverick, for example. At this point, there is no standard technique in the field, but I do envision there'll be a lot of work here, because with now Llama going towards mixture of experts, we'll see an even bigger wave in the field
towards MOE adoption. So, a lot of the dense models that are open weights and the ones that we're used to using on, the ones on a Hugging Face, for example, I think we'll see a huge trend towards more MOEs, and that will lead to a whole lot of this research. Because otherwise, they are just very difficult to load into memory. And although during inference time, you save a lot of costs, and even training and inference both becomes easier because you're only needing 17 billion active parameters, right? So training is easier and inferencing is easier, but the memory requirements don't go away. So that's cool.
I guess we are kind of running out of time. So if there is a quick question,
What can be the salvageability aspect of LLM?
Sorry?
Salvageability aspect, like how to prevent our model to get hacked or any kind of manipulation.
So there's a field of research looking into jailbreaking and prompt injections. Those are the two most common, security or issues with these models where they're able to we have papers where they're able to leak some of the training data from these models to so that's another case. But if you carry out jailbreaking, you're able to have the model bypass its alignment stages, where it starts talking about queries that it should not be talking about, something that was ingrained during alignment or in the training process, but seems to violate that, whatever it's learned, it seems to ignore that and start talking about, say, how to make a bomb, for example, right? Even though it was explicitly trained during, the alignment stage or to not talk about it. So jailbreaking and prompt injection are the two most common issues that we see. And there's a whole field of research talking about how to, protect these models against some of these attacks. So, whole world out there as far as jailbreaking and prompt injection.
Thank you.